Good morning. Today I am going to discuss about behavior of real gases. We know that real gases obey the ideal gas laws and the ideal gas equation PV equal to nRT only at relatively high temperatures and low pressures. But under other conditions of temperature and pressure, they show deviations from the ideal behavior. The extent to which a real gas deviates from ideal gas behavior is represented in terms of a function called compressibility factor or compression factor, which is represented by Z. Z is defined as Z equal to PV by nRT, where we know that volume by number of moles can be replaced by Vm. Vm represents molar volume. That is the volume occupied by 1 mole of the gas. Then what will be the value of Z for an ideal gas? For an ideal gas, Z equal to 1 under all conditions, and that will be independent of temperature and pressure. Thus, the deviation of the value of Z from unity for a real gas under different temperature and pressure conditions is a measure of its deviation from ideal gas behavior. So here we measure how much the value of Z deviates from unity for a real gas compared to ideal gas. So first one, extent of deviations from Boyle's law and Charles' law, that can be measured using Z versus pressure graphs. First we discuss the case of effect of pressure on deviations from ideal behavior. This is the plot. Here the nature and magnitude of deviations from ideal gas behavior is exemplified by a plot of compressibility factor versus pressure at 0 degrees Celsius for some of the gases. In this figure, we can see that we consider the gases like nitrogen, oxygen, hydrogen, helium, and carbon dioxide at constant temperature. From this graph, we can say that at very low pressures, Z is approximately equal to 1. At very low pressure, Z is approximately equal to 1, indicating the ideal gas behavior. However, as the pressure increases for gases like nitrogen, oxygen, and carbon dioxide, Z value first decreases and passes through a minimum. This is the case of nitrogen, this is the case of oxygen, and this is the case of carbon dioxide. All the three gases passes through a minimum, then increases continuously and eventually becomes greater than 1. That is the observation in the case of nitrogen, oxygen, and carbon dioxide gases. What are the inferences obtained from the values of Z? Here, Z value first decreases, which means each of these gases becomes more compressible than an ideal gas. Each of these gases becomes more compressible than an ideal gas. And what is the inference of Z value greater than 1? That is, each of them becomes less compressible than an ideal gas. Okay. So, if Z value less than 1 meant that each of the gases becomes more compressible than an ideal gas, whereas if Z value is greater than 1, which means each of them becomes less compressible than an ideal gas. Then, on the other hand, for helium and hydrogen, Z value shows only a continuous increase. Only a continuous increase with the increase in pressure. That is, for hydrogen and helium, Z value is always greater than 1 at all pressures, which means they are less compressible than an ideal gas at all pressures. If we know that if Z value is greater than 1, then it will be less compressible than an ideal gas. This shows ideal gas behavior is different from real gases, or real gases deviates from Boyle's law. Next is effect of temperature on deviations from ideal behavior. This plot again Z versus pressure plots of nitrogen at different temperatures. For example, we considering 50 degrees Celsius, 20 degrees Celsius, minus 25 degrees Celsius, minus 70 degree Celsius of nitrogen gas. What is the behavior of nitrogen gas under different conditions, under different temperatures? It is observed that the shapes of Z versus P plots change with the change in temperature. This fact shows that real gases deviates from Charles' law because it has different shapes at a different temperature. And another observation from the graph is the initial dip in the curve. This is the initial dip or minima. Dip in the curve is greater, dip in the curve is greater at lower temperatures, which means this dip decreases with the increase in temperature. When temperature increases, dip decreases. And at a certain temperature, here at 50 degrees Celsius for nitrogen, the minimum in the curve disappears. Here there is no minimum at 50 degree Celsius, and the curve remains almost horizontal where Z is about unity for an appreciable range of pressures. That is, at 50 degrees Celsius, in the case of nitrogen, shows Z value equal to 1 for a specific range of pressure, that is very low pressure range. That is from about 0 to 100 atmospheric pressure. That is the small pressure range in which Z value equal to 1 and there is no dip in the curve, and here Z value equal to 1. Within this range of pressure, that is 0 to 100 atmospheric pressure range, Boyle's law is obeyed at that temperature. Here in the case of nitrogen, the temperature is 50 degree Celsius. At that temperature and within that pressure range, Boyle's law is obeyed, and hence the temperature is called Boyle temperature. Not Boyle's temperature, boiling temperature. This is Boyle temperature, B-O-Y-L-E, Boyle. Boyle temperature. Or boil point, TB, boil temperature. Not boiling temperature, that is different. So what is the definition of boil temperature? Very important question. Boil temperature of a gas is the temperature at which it obeys Boyle's law over a appreciable pressure range. Over an appreciable pressure range. That is the important thing, and that pressure range will be very small pressure range. That temperature, that specific temperature is known as Boyle temperature. Here in the case of nitrogen, Boyle temperature is 50 degree Celsius. That is, at 50 degrees Celsius, nitrogen obeys Boyle's law at 0 to 100 atmospheric pressure range. Above the Boyle temperature, what will happen? Above the Boyle temperature, Z value increases continuously with the increase in pressure. Above that Boyle temperature, Z value increases. And below this temperature, below the Boyle temperature, Z value first decreases and reaches a minimum and then increases to above unity. That's about deviations, effect of temperature on deviations from ideal behavior. The next is deviations from Avogadro's law. We know that the volume occupied by 1 mole of an ideal gas at STP is calculated as 22.414 liters. If Avogadro laws were strictly obeyed, this volume will be independent of the nature of the gas. And 1 mole of any gas should occupy 22.414 414 liters at STP. But in actual cases, it is not true for any of the real gases, which means in the case of real gases, the volume occupied by 1 mole of gas at STP is not exactly 22.414 liters. There are some deviations from this value. For example, hydrogen shows molar volume at STP as 22.427. In the case of nitrogen, it shows 22.405. In the case of oxygen, it shows 22.394. In the case of carbon dioxide, it shows 22.264, etc. So, this behavior indicates the deviations from Avogadro's law for real gases compared to ideal gas behavior.